Imagine the universe. A vast expanse that stretches beyond our comprehension, filled with countless stars, planets, and galaxies. Each celestial body, a unique entity, contributing to the grand tapestry of the cosmos. Vast and filled with stars, planets, and galaxies. The universe is a complex and intricate system, where every element has its place and purpose. It's a marvel of organization and structure, governed by the laws of physics and the forces of nature. Now imagine the code within your computer. At first glance, it might seem like a chaotic jumble of characters and symbols, but much like the universe, it has its own order and structure. Each line of code, each function and variable, plays a crucial role in the overall system. It too is a kind of universe filled with data. This digital universe is built on the foundation of binary code, the ones and zeros that form the basis of all computer operations. Just as the universe is made up of matter and energy, the digital universe is composed of data and algorithms. Just like we need ways to organize and understand the cosmos, we need ways to organize data in our programs. Without a system to manage this data, it would be impossible to make sense of the information or to use it effectively. This is where the concept of data structures comes into play. That's where data structures come in. They are the frameworks that allow us to store, organize, and manipulate data efficiently. Data structures are the blueprints that guide the construction of our digital universe, ensuring that every piece of data is in its rightful place. They are the scaffolding of your code, the containers that hold and organize information. Without these structures, our programs would be disorganized and inefficient, much like a universe without the laws of physics to govern it. Without them, our digital universe would be chaos. Imagine trying to navigate a galaxy where stars and planets are randomly scattered without any order. It would be impossible to find your way, or to understand the relationships between different celestial bodies. Data structures provide a systematic way to store, retrieve, and manipulate data. They allow us to create order out of chaos, to build complex systems that can perform a wide range of tasks. From simple arrays to complex graphs, data structures are the tools that make it all possible. The right data structure can make your code more efficient, readable, and easier to manage. Choosing the appropriate data structure for a given task is crucial for optimizing performance and ensuring that your program runs smoothly. Just like astronomers use telescopes to study the stars, programmers use data structures to understand and manipulate data. By mastering these tools, we can unlock the full potential of our digital universe, creating programs that are both powerful and elegant. In Python, a list is like a cosmic address book. Imagine you have a magical book where you can store an ordered collection of items. Each item has its own unique position, just like stars in the sky. This is what a list in Python feels like. It's a way to keep things organized and accessible. It stores an ordered collection of items like a lineup of stars in a constellation. Each star has its own place, and you can find it by knowing its position. Similarly, in a Python list, each item has a specific position, or index, starting from 0. This means the first item is at index 0, the second item is at index 1, and so on. Each item in the list has a specific position, or index, starting from 0. This indexing system is crucial because it allows you to access any item in the list directly. For example, if you have a list of planets, you can easily find out which planet is at the first position by looking at index 0. Planets equals Mercury, Venus, Earth, Mars. Print planet 0, output Mercury. This simple line of code demonstrates how you can retrieve the first item in the list, which is Mercury in this case. Lists make it easy to manage and access your data efficiently. Lists are mutable, meaning you can change their contents after creation. This is one of the most powerful features of lists. You can add new items, remove existing ones, or modify the items as needed. This flexibility is what makes lists so versatile and useful in programming. You can add, remove, or modify elements within the list. For instance, if you want to add a new planet to your list, you can simply use the append method. If you need to remove a planet, you can use the remove method. And if you want to change the name of a planet, you can directly modify the item at the specific index. This flexibility makes lists incredibly versatile for managing dynamic data. Planets append Jupiter. By appending Jupiter to the list, you have now expanded your collection of planets. This dynamic nature of lists allows you to handle data that changes over time. Add Jupiter to the end. This simple action shows how easy it is to expand your list. Whether you're dealing with a small set of items or a large collection, lists provide a straightforward way to manage your data. Planets 1 equals Venus, evening star, modify an element. By changing Venus to evening star, you can see how lists allow you to update your data as needed. This ability to modify elements is essential for keeping your data current and relevant. Common methods for lists include append, insert, remove, index, and many more. These methods provide a wide range of functionalities that make working with lists efficient and effective. Whether you need to add new items, find the position of an item, or remove an item, there's a method for that. These methods allow you to manipulate lists with ease. By mastering these methods, you can handle complex data structures and perform various operations on your lists. This makes lists an indispensable tool in Python programming, enabling you to write more flexible and powerful code. Imagine a vast library filled with books organized by subject. Each section is meticulously categorized, making it easy to find exactly what you're looking for. This is the essence of a well-organized system, and it's a perfect analogy for understanding how dictionaries work in Python. That's what a dictionary is like in Python. Just as a physical dictionary contains words and their definitions, a Python dictionary stores data as key-value pairs. Each key in the dictionary is unique and is used to access its corresponding value. It stores data as key-value pairs, where each key is like a book's title, and the value is its content. This structure allows for efficient data retrieval, as you can quickly look up the value associated with a specific key without having to search through the entire collection. For example, consider a dictionary that stores information about stars. You might have entries like Sun G-type main sequence star, Sirius binary star system, Betelgeuse, red supergiant star. If you want to know more about Sirius, you simply look up the key Sirius and get the value binary star system. This makes accessing specific pieces of information incredibly efficient. Unlike lists, dictionaries are unordered, meaning the elements are not stored in a specific sequence. This unordered nature allows for faster lookups, as the position of the elements doesn't matter. Instead, the focus is on the keys and their associated values. Instead, you access values by their keys, making lookups very fast. This is particularly useful when dealing with large data sets, as it allows you to retrieve information quickly without having to iterate through the entire collection. Let's say you discover a new star, Proxima Centauri, which is a red dwarf star. You can easily add this new entry to your dictionary. Just like adding a new book to a library shelf, you simply assign a new key-value pair to the dictionary. Dictionaries are mutable, allowing you to change, add, or remove key-value pairs. This flexibility makes them incredibly powerful for managing dynamic data. You can update the information as needed, ensuring that your dataset remains current and accurate. They are perfect for representing structured data and relationships between different pieces of information. Whether you're mapping user IDs to user data, storing configuration settings, or managing any other type of structured information, dictionaries provide a robust and efficient way to handle your data. Moreover, dictionaries can be nested, meaning you can have dictionaries within dictionaries. This allows for even more complex data structures, enabling you to represent hierarchical relationships and multi-level data in a clear and organized manner. Error handling with dictionaries is also straightforward. If you try to access a key that doesn't exist, Python will raise a key error. However, you can use methods like get to provide a default value if the key is not found, making your code more robust and error-resistant. Additionally, Python offers dictionary comprehensions, which allow you to create dictionaries in a concise and readable way. This feature is particularly useful for generating dictionaries from lists or other iterable data structures, making your code more efficient and easier to understand. In summary, dictionaries in Python are like your code's personal library. They provide a powerful and flexible way to store and manage data, making it easy to access, update, and organize information. Whether you're working with simple key-value pairs or complex nested structures, dictionaries are an essential tool in any Python programmer's toolkit. Imagine using a telescope to observe a specific type of star, filtering out all the rest. Sets in Python work similarly. They store a collection of unique, unordered elements. Observe planets equals Mars, Jupiter, Saturn. Print Mars and observe planets. Output, true. Sets are mutable, but they only contain unique elements. Adding the same element twice has no effect. Observe planets add Mars. No effect, Mars is already present. Sets are excellent for tasks like eliminating duplicate entries from a list or checking for membership. They are also efficient for mathematical set operations like union, intersection, and difference. Think of physical laws of the universe, constant and unchanging. Tuples in Python embody this concept. They store an ordered collection of items, but once defined, they cannot be modified. Coordinates equal sign, 10.5, 20.3, print, coordinates 0, hash output, 10.5 tuples are immutable, meaning you cannot add, remove, or change elements after creation. This immutability ensures data integrity. Coordinate 0, equal sign 15.2 hash, this will raise an error. Tuples are often used for representing fixed collections of data, like coordinates, dates, or configuration settings, where immutability is desired. Just like an astronomer selects the right telescope for observing different celestial objects, programmers choose data structures based on their needs. Each structure has its strengths and weaknesses. Lists excel when you need an ordered collection of items that you can modify. Dictionaries shine when you need to store data with key value associations, allowing for fast lookups. Sets are perfect for working with collections of unique elements and performing set operations. Tuples are ideal for representing fixed collections of data where immutability is crucial. Imagine tracking the trajectory of a spacecraft. You might use a list to store its coordinates at different points in time. Trajectory equal sign, 10.2, 5.6, 12.8, 7.1, 15.4, 8.9. To store information about a star, like its name, distance, and spectral type, a dictionary would be a great choice. Star_info equal sign, name Sirius, distance, 8.6, spectral type, A1V. To efficiently find all the unique elements in a large data set of astronomical observations, a set would be the most suitable. Observations equal sign, galaxy, star, planet, galaxy, nebula, star, unique _observations equal sign set observations. Just like understanding the fundamental laws of physics is crucial for comprehending the universe, mastering data structures is essential for writing efficient and effective code. Lists, dictionaries, sets, and tuples are your building blocks. By understanding their strengths and weaknesses, you can choose the right tool for the job and bring order to the vast universe of data within your programs.